Okay, so we're doing internal loads. And the last thing we have to talk about is distributed loads. And those show up in something like this. So if you have a cantilever beam, instead of the loads being applied just at a single point, you could have something like this, where the load is spread out and distributed in some prescribed way. So here, let's say that we have 10,000 newtons per meter. And what this means is there is not a finite point force applied by this distributed load at any point. That's all messed up. Distributed loads don't apply a finite force at any point. To apply a finite force, this distributed load has to be spread out over some finite interval. So applied over a finite interval. Okay, so what's the point force that's applied by this distributed load at the end here? There's no finite force, but if you take some small chunk of the end and multiply this distributed load by the interval, say you take a centimeter here at the end, the distributed load over that centimeter is basically 10,000 newtons per meter over the whole thing. And so the total force would be 10,000 newtons per meter times 0.01, that interval, and then that would give you a finite force. I think a good comparison to that is like the relationship between like speed and distance traveled. You can, when you're driving, you can go different speeds, but how far do you go at any one instant? There's no distance traveled in a single instant. You need to be going that speed for some finite amount of time. It works the same here. Okay, so the force, so what we're going to do with distributed loads is we'll treat distributed loads as point forces. And to do that, the total point force, the magnitude of the point force, is the area of the distributed load shape. And the location of the point force is the centroid of the shape. Okay, so let's use the example above. Mm-hmm. Just to there? Lower? Okay, so this has a length of 3 meters. And the distributed load is 10,000 newtons per meter at the right end, 0 at the left end, and it's linear in between. And we want to calculate the reaction loads at the wall. Okay, so I'm going to draw a free body diagram of the beam. I didn't give any information about the mass, so we're just going to leave that out. This fixed joint at the wall applies a force vector, call that R, and a couple, I'll call that MR, the reaction moment. And then to figure out how to treat this distributed load as a point force, we're going to think about the shape. And this shape is a triangle with a base length of 3 and a height of 10,000. That looks sort of weird. It's obviously not drawn to scale, but still, we're just going to use this to calculate the area and then where the centroid is. So the area of this is base times height over 2. So 15,000. And that's newtons. And the centroid location is a third of the way from the, so a right triangle, whichever direction you're looking at it, always one side is a point and one side is a wall. You know, it's a third of the way from the wall towards the point. So we know that this distance is 1. And now I can use that information here. So the total force is the area, 15,000. And this distance is 1 meter. And then use Newton's laws. Newton's second law says Rx, Ry plus 0, negative 15,000 is equal to zeros. So R is equal to 0, positive 15,000. And the moment equation says, so I'll put my about point here. We have the moment MR, the reaction moment. And then the 15,000 Newton force has a moment arm of 2 meters. And would that force make it rotate clockwise or counterclockwise around that point? Clockwise, so it's negative. So negative 2 times 15,000 equals 0. MR is equal to 30,000 Newton meters. Okay, so we need to know the centroids of a few shapes. Here's a list of the, I guess, just the 3 centroid shapes that we're going to use. So centroids of common shapes. The first one is a triangle, right triangle. So this is 90 degrees. This is the base, this is the height. And the area is base times height over 2. I'll call this distance x bar. And this distance y bar. X bar is equal to b over 3, and y bar is equal to h over 3. And the second one is for a quarter circle. With a radius r. So I'll call this distance x bar and this distance y bar. The area of this shape, it's a quarter of a circle, so pi r squared over 4. And x bar and y bar are the same, and those are 4r over 3 pi. And then the third shape is a half of a parabola. That's x bar. That's y bar. I need to give dimensions. So the horizontal length is h, and the vertical is a. The area then is 2ah over 3. X bar is 3h over 5. And y bar is 3a over 8. Okay, so now let's use this same idea. We used the representing a distributed load as a point force to calculate the reactions at the wall. So now let's use that same example and use the same idea to calculate the internal loads in that beam. So I'm going to start with a free body diagram of the whole thing so we know what the loads are. We have this distributed load where it's 10,000 newtons per meter at maximum. At the wall, we have an upward force of, what was it, 30,000? 3 times 15,000. What do we get for the couple? 30,000. Okay. So now we have to choose, to start doing the cuts, we have to choose where the boundaries of the subfunction are going to be. So remember that the boundaries of the subfunction will be at endpoints, so those first. And then other locations will be places where there are point forces or point couples or places where the distributed load function changes. So there is a point couple and a point force, but those both are at the same point, and we've already dealt with that point. So we don't have to deal with that point again. Is there anywhere else where any of that's happening? No. So we only have 2 of these points where the subfunction can change. And so we have 2 minus 1 cut that we have to do. So this 1 cut is going to represent the whole beam. That music's really loud. Good. The music, I like it. Makes me feel like I'm in a movie about a teacher. Like a teacher who turned out to be a real hero after all. Yeah, exactly. Active shooter. I learned about this watching parkour videos. Okay, so cut 1 is valid for all x's on the whole thing, so between 0 and 3. I'm going to call 0 to 3 Texas because it's where all my x's live. That was stupid. I really thought that was going to get a better reaction. Like, no, that song, All My Exes Live in Texas. Oh, like an old country song. Okay, so I'm in the light blue, I'm going to draw all the things that aren't happening on the piece that we're isolating. Okay. So we've made our cut, and the cut has a length of x. We have a force of 15,000 and a couple of 30,000. We have this part of the distributed load, and then we have the internal load, so T, V, M, and torque. Okay, that's everything. And so now the only problem is what we're doing now is exactly the same as what we did to calculate the external loads on the left end, except now the unknowns are over here. And then there's one other thing that we have to deal with. We know that over here, the distributed load is 10,000. But that's not the same as it is here. In general, like the magnitude of that distributed load at the right end of our cut is going to be somewhere between 0 and 10,000, and it's going to depend on x. So we just need a way to represent what the value of that distributed load is at the value x. And the way we're going to do that is, notice that for any x value, the height of this distributed load is going to follow the function y equals 10,000 divided by 3, that's the slope, times x. That's the equation for that line. When x is 0, the height is 0. When x is 3, the height is 10,000. And it's a linear function. Okay, so that means that the height at the value x, which is this, is 10,000 over 3 times x. So 3,333x. And now I'm going to draw a new free body diagram, but represent that chunk of the distributed load as a point force. Okay, so here's that piece. We still have the force and the couple on the left end. We still have the internal loads. And now we have to calculate the area and the centroid of this triangle, where the base is x and the height is 3,333x. Okay, so the area of that triangle is base times height over 2. So 3,333x squared over 2. 1667x squared. And the centroid this distance is x over 3. Sort of hard to read. Okay, so this is x over 3. The area is 3,333x times x over 2. And so I'm going to represent this now as a point force with a magnitude of 1667x squared. And then since this is the about point, what we really want is the distance from here to here. If the whole thing is x, and this is x over 3, what's this distance? Yeah, 2x over 3. Okay, so Newton's second law says 0, 15,000 plus 0, negative 1667x squared plus t negative v is equal to zeros. So t is equal to 0. V is equal to negative 1667x squared plus 15,000. And then the moment equation about the z-axis, we have the couple of positive 30,000 we have the downward force of 1667x squared with a moment arm of 2x over 3. And would that make it rotate clockwise or counterclockwise? Yep, clockwise. So negative 2x over 3 times 1667x squared. Then plus m minus vx is equal to 0. So m is equal to negative 30,000 plus 1111 x cubed, I think, right? And then plus vx. And we can substitute the function that we got for v in for v in that equation. So we get negative 30,000 plus 1111 x cubed minus 1667 x cubed, because we're multiplying v times x, plus 15,000 x. And we can group the two x cubed. So the bending moment is equal to negative 555 x cubed It's 5, right? Yeah, I'm going with the subtraction here because of that negative sign. That's what the negative sign means. It's one what? Oh, yeah. It's this repeating. This is shorthand for 5's repeating forever. Okay, yes. Okay. And then plus 15,000x minus 30,000. This problem didn't have any external torque, so if you do the rotational equation about the x-axis, you just get that the torque is equal to 0. All right, and it would be a pain to try to plot these functions by hand, but you could plug that into a calculator or a Desmos or something, computer, see what it looks like over the whole length of the beam, and then that would give you a sense of where you're concerned about the beam breaking.
If we saw something that would be a concern with beam breaking, how would we adjust for that?
You could make the beam thicker, or what? In fact, I guess we'll see when we talk about how to get the stress, how to take the internal loads and calculate the stresses from them. We'll see what kinds of things affect the stresses, and then you'd be able to see what kind of changes to the shape would, no, we'll get to that, I guess. So here are a bunch of things that need to hold, and you can use these as checks on your values. on your tension, shear force, bending moment, and torque. First, at each point, the derivative of the bending moment with respect to x is equal to the shear force. Also at each point, the derivative of the shear force with respect to x is negative q, where q of x is the distributed load function. I'll go through all these with the example after I'm done with this. Third, the bending moment is equal to 0 at an endpoint if, only if, there's no point couple at that endpoint. Fourth, the tension is equal to 0 at an endpoint if and only if there's no horizontal point force at that endpoint. Anybody want to guess what 5 and 6 are?
Other facts.
They sort of follow a pattern with 3 and 4. Yes. Shear force, right? So, well, yeah, let's do that one. So the shear force is 0 at an endpoint if and only if. What do you think this one will say? Yes. There's no vertical point force at that endpoint. And then the last one? Torque, yep. So the torque is equal to 0 at an endpoint if and only if there's no point torque at that endpoint. So that's a lot of stuff to go through, 6 of these checks. I'm usually, I suppose, too lazy to go through all 6, but I definitely always check the first 2. Check those 2 derivatives and make sure that it makes sense when you take the derivative of the bending moment function, that you get the shear force function, and that when you take the derivative of the shear force function, you get the distributed load function. I'm going to go through these all here. I guess I'll go through all 6 now. If you have a problem that you have to get right, like, you're really doing this for a research project or for, work or whatever, then you want as much information as possible, so you go through all these. If you're just going to turn it into me.
Just say there's 6, we'll have a computer do it.
Yeah, have the computer do it. You just have to write the program. That's the.
So that's.
Yes, that's right. Someone just skipped 3 through 6.
So in a job, we will actually do these for every report that we file, or every.
I have no idea. I mean, I think that stuff varies so much. I mean, I'm sure there's jobs where people do some of this kind of stuff. This is sort of a way of thinking about the internal loads and beams that's applicable to in a bunch of different areas, but yeah, I mean, I think there's a lot of range to what kind of job. I mean, so yeah, mm-hmm. Yeah. Well, that's sad. That's just sad. Okay, so let's go through these 6 checks on the example we just did. So first, so this is the example above. So our bending moment function was equal to negative 556x cubed plus 15,000x minus 30,000. Okay, so dm dx as a function of x is negative 1667 squared plus 15,000, and that is equal to v. Where is it? Okay, so this one, check. Don't get too excited yet. Still 5 to go. That's true. Okay, so the shear force function is what we just wrote. Negative 1667x squared plus 15,000. So dv dx is equal to negative 3333x and so now we want to compare this to the distributed load function. So what is the distributed load function, you may ask? Yep. So that's this. So this is equal to negative, nope, Q. Check. And now at the endpoints. So the first one we're going to think about is, what did I say, the moments first? Ending moments? Yeah. Okay, so if there's any endpoint where there isn't a force point couple, then we expect the bending moment function to give us 0 at that endpoint. Okay, so here's the distributed, or here's the Freebody diagram of the whole thing. There is a point couple on this end. So this is going to be non-zero for the bending moment. But over here, there's no point couple. So the bending moment has to come out to be 0 here. So the way to check that is to plug those x values into the bending moment function. X equals 0 over here. So plug in x equals 0, you get negative 30,000. So that's non-zero like it should be. Then plug in x equals 3, and you get 9 times negative 5 plus 45,000 minus, yep, 0. Check. Then horizontal forces. T should be equal to 0 at both endpoints because we don't have any horizontal forces. And where is it? T is equal to 0. There's not any function there, so that one works. So at both endpoints, T is equal to 0. And then shear force. So where would we expect there to be a non-zero shear force on this? So for x equals 0, yeah, we'd expect that shear force to be non-zero because we have this vertical point force. There's no vertical point force here. There's a distributed load, but remember that distributed load applies infinitesimal force at that point. So we expect V equals 0 there, not 0 there.
Is it because that is attached to the wall?
Yes, the wall is applying that vertical point force to the beam. So plug 0 in for V, and you get V is 15,000 on the left, so that is what we expected. And plug in 3 for X, you get 9 times this. Yeah, that's probably about 0. So that one works. Yeah, sure. You can write whatever you want.
Have you ever messed up a test intentionally, like when you were in college and just said, this should be this because, you know, I just noticed this?
No, I definitely never did that on purpose, but I'm sure I said things like that occasionally because I didn't have anything better to say, you know? Yeah, exactly.
I have to write something, so let's do that.
So torque now should be equal to 0 at both endpoints. And we didn't have any torque in any of the problems, so that one works.
But as soon as you throw a wall on that right side, then that doesn't become true.
That's right. Well, if you put a wall on the right side and didn't change anything about the loads, well, yeah, if you put, so here's what would happen if this was also a wall. You had this beam in between two walls. First, maybe most importantly, it would be statically indeterminate. You know, let me show the, and that is because you get 3 variables from 3 variables of load on the left side because of the fixed joint. You get 3 more variables on the right side. You only have 3 in 2D, you only have 3 equations from Newton's laws. So you'd have 3 equations for 6 variables. And using statics, you can't solve that. Okay, so that's called statically indeterminate. But this idea that we're using now, later on in the class, is going to give us a way to do calculations like that, using what we know about the deformation of that material. And so, but yes, if you put a wall here, some of the load would be taken by this wall, some would be taken by this. You'd have non-zero shear forces at both ends. Okay. Let's do one with weight. Okay, so let's say that we have a beam connected to a pin joint at the left and a roller at the right. And let's say that this beam has a mass of 50 kilograms. Let's say this is 2 meters. And we want to calculate the internal loads. So first we have to calculate the external loads. A free body diagram, there's the beam. And you have an unknown force vector on the left, call that RA. And then from the roller, you just have an upward force, call that RB. And then the weight force, we can treat as a point force acting at the center of mass. So that's 50 times 9.81, so 490.5. Okay, I have an important question here. How do we know when we can go from an a distributed load to a point force? Like, we had the weight is a distributed load, right? And now when we get the free body diagram, I treat it as a point force. Then in the last problem, when we did the cut, I went back to treating it as a distributed load, drew a free body diagram. Well, the key thing is once you choose the body to isolate, only then can you represent the distributed load as a point force. Okay, so now that I've chosen to isolate the whole thing, then I can say, okay, I'm going to treat it as a point force at the center. But and I'll show you why that would cause a problem if you say at the start said, I'm going to treat the weight as a point force acting at the center, and then you did your cut and did the cut before you got to where that weight is applied. That would mess up your answers. Okay, so Newton's second law says RAX RAY plus 0, negative 490.5 plus 0 RB is equal to zeros. And the moment equation, I'll use this as the about point. This is acting 1 meter away from the about point. So, and that would make a clockwise rotation. So we have negative 490.5 plus 2RB is equal to 0. So RA is equal to 0, 245.25. And RB is 245.25. So now we have to think about how many cuts we need. If you look at this picture, that is the last picture that you would have drawn in this problem, there's a good chance you're going to think that there are 3 points where these subfunctions could change. So don't do that. That's wrong. This is not a real force. That point force is just a mathematical thing, the mathematical way that we're treating that distributed load. So we want to go back to the original picture. And there's point force here and here. The same distributed load acts over the whole thing. And so we just have n equals 2, and we just have to do 1 cut. I guess I'm not going to finish this problem. Let me just draw what the cut looks like. Ooh, is it? Ooh, I know what we're having for dinner. National Pizza Day? Yeah, right. Oh, everyone's going to be at the pizza place. Perfect time for tacos. So this is for any x between 0 and 2. So I'm going to stop drawing this pretty soon, but just to give you an idea of, so there's still this thing going on over here that is not included in our free body diagram. And then there's the upward force of 245.25. And then the internal loads, T, V, M, torque. The last thing we have to do is figure out what this distributed load is. We know that the total weight is 490.5. That total weight is spread out over 2 meters. And so this distributed load is 490.5 over 2, or 245.25 newtons per meter. Okay, so now we can treat that distributed load as a point force. We have a rectangle with length x and a height 245.25. So the area is 245.25x, and the centroid is right in the middle. So another free body diagram. We have the piece we're isolating. We have the force from the pin joint. We have the weight force of 245.25x. You know that that has to depend on x because the amount of weight you're dealing with depends on how much of the beam you're considering. And then the internal loads, T, V, M, torque. Any questions about that? We'll do some more examples on Monday. In this class, that's right. Quiz on Monday. Yep.
This will be on.
Yes. Yeah, up through today.